はい、皆さんお待たせいたしました。それでは時間になりますので、次のセッションに、移らさせていただきます。今回お二人でご登壇いただきまして、40分間のセッションとなっております。まず皆さんから見て、左手側ですね、初ジョイさんと、お隣の、コリーさんです。では、お二人による、作って学ぶエクステンシブルエフェクツです。どうぞ。
So I'm Kory from Alp, and
I'm hsjoihs from Duango. Nice to see you.
nice to see you. So I'm very thrilled to be here, both as in frightened and as in excited, since it's the first time for me speaking in front of so many people and for such a long time. But let's not waste time seeing me being frightened, because we have a lot to cover. And so hang tight and enjoy the talk. Okay, so before anything, let me first tell the talk itself to you. Okay, so first of all, by effect system, people either refer to mechanisms for tracking what kind of side effects may occur in a program, or a bit more loosely to a general framework that provides non-native language constructs by specially handling side effects. And recently, the idea of effect systems is just becoming a hot topic in general. And although personally, I think it always has been a hot topic, especially because new approaches and libraries aimed at practicality are emerging. In Scala community, for instance, we've had Atmos.org EFF for quite some time, several years already, but more recently, a library called Kyo, spelled KYO, that's targeted at Scala 3, is gaining quite some attention for its ergonomic handling of effects. And if you look outside the Scala community, we can see that the effect.ts library or effect.ts ecosystem is emerging within the TypeScript community. It's probably a nice time to have a look at the principles behind all these libraries. And for that, we'll be looking at a simplified version of an effect system, which is commonly known as EFF. It's often pronounced F, but I'm just going to read it EFF this time. Okay, so we'll be looking EFF inside out. And what I mean is, instead of trying to sort of sell you the EFF by telling you what it's capable of doing, we'll sort of guide you through a story. It's a non-historical story that somehow naturally leads to the construction of EFF. So the goal of today's talk is that you'll be able to design your own EFF library, a simplified one though, and intuitively grasp its capabilities and limitations. Okay, why EFF? I claim, it's a big claim, I claim that EFF is one of the simplest effect systems out there. And I believe that understanding the internals of EFF will also help you guide through internals of other purely functional effect systems, like Cat's Effect IO or ZIO. There's some technicalities, but I won't read through that. So in the end, the story which I'm going to tell you is just quite interesting on its own. And even if you know a particular implementation of an effect system, I'm pretty sure it's going to give you a fresh perspective on how one could perceive effect data types. Okay, so the first thing we should do is tell you what we have to do. So to begin with, what I want you to imagine is this generic situation in which a machine that's depicted in the middle loads a program drawn on the right, the blue one, from somewhere else, and then interacts with the world by performing inputs and outputs as directed by the loaded program. This structure is overwhelmingly prevalent in all layers of abstractions of computation, and the machine could be a VM that's loading a bytecode and invoking the native APIs provided by the operating system, or on the very opposite side of the abstraction spectrum, the physical collection of semiconductors receiving voltage signals and in turn outputting voltage signals. say, 2 machines, even though they're as tiny as things could get. Anyways, this structure occurs everywhere. And I want you to acknowledge this pattern for the next few minutes. I'll come back to this shortly. Okay, so for a brief moment, we'll put aside the machine program world triple thing. And now I would say that pretty much any purely functional effect system rests upon the following slogan. The slogan saying that eagerly causing side effects is potentially a premature concretization. The talk on the right elaborates on this idea very well. And my favorite analogy presented in this talk is that causing side effects on the fly is like trying to control explosion in Minecraft instead of first splicing all TNT blocks and then detonating everything from a safe distance. The talk on the left, on the other hand, which was the first talk of last year's Scala Mastery, I believe, that's an excellent talk explaining practical consequence of this slogan. Now, this is a big premise. It's such a big premise that I don't think it is universally applicable to all software. As a matter of fact, some of other talks we're hearing in the Scala Mastery 2024 are also suggesting that not all apps can really benefit from delaying this concretization. Nevertheless, to keep the story rolling and to enable you to assess if this slogan is useful, let's pretend for now that we wholeheartedly accept it. Okay, so by doing so, we're now forced to go into a path that seems rather indirect. I mean, it is indirect. To see that, we should go back to the diagram before. Now, if we don't want the program to eagerly perform side effects, what do we do? Well, what the slogan wanted to remind us is that we shouldn't be throwing away compositionality if we don't have to, or if we don't have a reason to do so. So instead, we treat programs as values, which means we'll have to design a data type to represent programs, which means we'll have to design a machine that in turn consumes these programs to perform actual side effects. We are essentially recreating the right half of this diagram entirely within Scala. Okay, so by mechanism to run the executable, I really mean something as concrete as a class. Let's name it machine, that's got a single method run, which takes a program or executable and performs something according to the program and returns something as the program indicated to. Okay, so we need to build 2 things: a data type representing programs and machines that consume them. It's probably more sensible to first create models for programs and then create machines. It's easier that way, and that's exactly what we're going to do. But here you'll encounter the first question or problem-ish. As I mentioned, the relationship between machines and programs are just ubiquitous. And as you might have guessed, they're also extremely diverse. So what kind of program should we model in the first place? Well, for today, I suggest as a guide of this talk, we start with models of assembly programs of all things. And then we're going to introduce 2 key enhancements to the assembly model, with which magically we will have been led to the model of EFF. This might sound out of the blue idea, but believe me, this is going to work. After we have the model EFF at hand, we're now going to turn to the interpreter, the machine that's able to run EFF programs. Okay, so some of you may have been introduced to EFF as a rather magical functional programming technique to mix in and track different kinds of effects in your program. And that's also true. But today's main point is EFF really is a model of programs that actually closely resembles assembly languages of all things. We'll see why that's the case. So now my friend hsjoihs, he's able to tell us something about the assembly language in general.
Okay, so let's learn stuff from assembly, which is, for our purpose, the most important model of programs. So the assembly language is a language of sequential structure. Have you ever heard of it? It's not a single language, it's a family of languages that are sequential. So we have no curly braces, no nesting. All you do is to list one instruction after another. So if you need loops, you simply jump back to the start of the loop. You need branching, then you just need to conditionally choose whether to jump. And that's it. So simple and clear cut. Okay, so let's see some real world examples. So first of which is RISC-V. Here there are 3 instructions, each representing multiplication, subtraction, and bit AND. And then running these sequentially would result in the data stored in places called registers, A0, named A0, A1, and A2, to be modified to suit our needs. So here's another example, x86-64, which denotes exactly the same thing, but the names of the registers are different. Now it's EAX, ECX, and EDX. Finally, JVM that we all love. So in JVM, unlike the ones that we've seen before, implicitly operates on a stack, and you either push some value onto the stack or pop some value from it. And then by sequentially executing these simple commands, we can do whatever we want to do. Okay, so assembly is the language of sequential structure. So that means that it's quite natural to think of those as the list of instruction for some complicated data type instr. And this looks like a good way to represent the assembly language program in Scala. Well, and this looks perfectly fine, and some kind of programs are best suited to be represented like this. However, but this is a big but, there lurks a problem. So let's see the JVM example one more time. You see the line numbers on the left, 0, 1, 2, 3, 5. Okay, what happened to 4? Well, actually, it turns out that these are not so simple, or maybe too simple. It turns out that they are made up of bytes, and then the numbers before each line actually represented the byte offset. So this notion is completely lost in the list structure. So why does this thing matter? Well, didn't we just abstract it out? Do we even need to care? Well, introducing branch instructions, the destroyer of sequential execution. So we want, or we need, branch instructions because, well, without them, we can't have if and while, and everyone needs if and while. So here are the 3 examples from the assembly languages that we've shown. So let's focus on the JVM on the left. So this if icomp EQ reads from the stack and decides whether to jump, but it has some 9 something. What's this 9? It turns out that, well, it's the byte offset. It stands for the destination, and it is counted in bytes. So we can see that the line numbers are now 0, 1, 2, 5, 6, 7, 8, 9, 10. And there's a technicality that I won't mention. Okay, so another important aspect is that we never want to step into the middle of an instruction. So we've seen the x86-64 instructions, and each of them are composed of like multiple bytes. Okay, what if you jump to the middle of an instruction? Well, a horrible thing happens. Well, you get some kind of nonsense SCAS, shift right, something that you probably did not want or did not expect. So we definitely do not want to step into the middle of an instruction. So list instruction combined with destination in bytes is an extremely troublesome model. Well, as mentioned in like one of the yesterday's speeches, make legal states unrepresentable. That's what we want. So list instr plus destination bytes violates that principle. So we do not want that. And another complaint that we can make is that it makes it very hard to edit or refactor, or at least tedious to do so. So like every time you change some little bits and it changes how many bytes the one branch is made up of, then you have to painstakingly change the encoded destinations. If you want to compose two things, you have to change the destinations. They are not nice. They are nasty. So we want to use a different structure that mitigates these issues. Okay, so introducing the graph model of assembly languages. Instead of writing by 9 that points to the line number 9, we prefer representing this as a graph. So this would be much nicer. So there is a technicality that I will ignore. There's a technicality of technicality that I will ignore. Okay, so this is Scala Matsuri. So I will finally be talking about Scala. So let's write the assembly model in Scala. So before trying to represent the entire assembly program, we'll first focus on modeling individual instructions. As an example, consider an instruction set that contains the increment instruction and a branch if equal to 0 instruction. Well, to distinguish between branching and non-branching instructions, we encode the branching property of each instruction in the branch index type. For example, we encode the fact that inc does not branch by labeling inc instructions with branch index equals unit, since unit is a type that has a single value. On the other hand, the branch if equals 0 instruction does branch. So we encode this fact by specifying the branch index to be Boolean, because Boolean has precisely two values, true and false. So we are essentially giving out indices to the outgoing edges. This enables us to identify jumping and non-jumping execution paths. But not only that, it also precisely specifies and enforces how much an instruction can branch. So is that all? No. Well, you see the enum. This is not yet a graph. It's a single instruction. That means we need a graph-shaped container, which we will name executable, into which we put instances of instr1. Okay, but before we proceed, we'll slightly enrich the structure of our language. Specifically, so far, we didn't have a way to mark the end of a program. In the real-world assembly, programs usually terminate by following some sort of procedures defined by operating systems. Yes, it's possible to design such a protocol, but it's a lot more straightforward if we simply allow the program to express the end of the program, much like the nil indicates the end of a list. So just like iList has a nil variant, we will add a special type of node called exit. An exit node is holding the exit code, which will be the result of the entire program. And the node never has an outgoing edge to another instruction or to an exit node. So therefore, the container is made up of two types of nodes containing instructions and the exit nodes. We refer to a node containing an instruction as non-empty because it is a representative of a non-empty program. Okay, let's write down the idea in Scala. Finally, we find that the executable data type, standing for graph instructions, is an enum of exit and non-empty. Well, let's now inspect the details. Executable has two type arguments, one specifying the instruction set, and another one specifying the type of potential exit codes of the program. The exit node is exactly as we defined. It holds a single exit code and nothing else. A more interesting enum variant is the non-empty case. The first field is the instruction that occurs at the very beginning of the program. This is like a head of a list, so we can call it a head instr. The second field is a bit tricky. Recall that we are using branch index as identifiers of edges going out from an instruction node. So the non-empty case should hold as many executables as transition targets as there are branches. hence as many values there are of the branch index type. To express this, we are simply holding a function from branch index to executables. So really, we are regarding the function as a collection of executable that is indexed by values of branch index. This is why we are calling the branch number type branch index. Okay, so let's see the actual way to construct an instance of an executable. So let's have this kind of simple program. And if you want to write in Scala, this will be the code that fulfills. And so let's see that. So the first node, inc A0, so that is a non-empty node that contains inc A0 as the instruction. And then it takes a unit value and points to a value named P that we will define in the above. So the definition of P is like this. So we have branch f equals 0, A0, and it has two branches, true and false. So when it's true, then it points to the exit node that has 42 as its exit code. If it's false, then we have two more non-empty nodes. So non-empty of inc A2, followed by which contains as the following program, the inc A0 non-empty node, which points right back to P. So that's why we have lazy val, because we want it to loop. Okay, so we've so far we've only seen examples where branch index is either a unit or a Boolean. However, in principle, there's nothing preventing us from putting other types as branch index. For example, if we define an enum comp to have 3 values, then the moment we put comp as the branch index of an instruction, we will have a 3-way branching instruction. If we take this idea to the extreme, we can even put large types like int or even infinite types like big int or array byte. We can put those as branch index types. Well, the analog of such branch indexes in assembly would be like 4 billion distinct jump targets, or even infinitely many jump targets attached to a single branching instruction. Well, unless you're governing the galactic empire and has an infinite petabytes of RAM, such an assembly program is a nonsense. However, because the branches field, the collection of branch indexes, is a lazy collection, we actually end up not occupying much RAM, even if branch index is something like int. As we will see in the example at the very end of the talk, we can reinterpret branch index as a return type of the instruction. And with that, the assembly suddenly looks like a normal imperative language. So shoving an arbitrary type into the branch index type is our second enhancement to the model of assembly programs. And we are done. The executable data type is EFF, except for a few technicalities. But for the remainder of this talk, we'll keep calling the program data type executable because that's what it is. So, okay, so let's talk about composing the executables that we've made. So the best way to do that is to think of a function inject at exits. So, which is a function that replaces all the exit directives in an executable with programs to be executed subsequently. So we have the program on the left, which either exits with exit code 1 or 2. And you combine that with a function that maps the exit code to an executable, then what you can do is to put these graphs and combine them together to make a new executable. So this is quite different from like piping in Linux shell, since piping does not build a new program. It simply instructs the shell to connect the standard output into standard in. On the other hand, inject at exits is a very low-level operation that takes an executable graph and builds another executable by appropriately choosing programs to be concatenated according to the exit code of the previous program. So this is the implementation of inject.exits. We will not go over this because it's a little bit, well, you can read it after the talk. Okay, so let's bring the microphone back to Kory.
All right, so we're done modeling the programs. Good. We have been talking about how nicely primitive and composable executables are. However, defining and manipulating forms prove useful only if we can come up with nice semantics. A program without the corresponding runtime is like a car without an engine. So we need a way to give EFF programs meaning. That's our next topic. Okay, so I'm first going to talk about some general stuff. Some instructions are more fundamental and more powerful than others. So for example, some x86 instructions like move, XOR, or add, they're known to be capable of running any computation. Like literally they are Turing complete on their own, albeit with huge overhead. Somebody actually has implemented a C compiler that translates your C program into a stream of move instructions. Please have a look at it. It's really, really interesting. So, but on the other hand, some instructions like AES inc, that's a single round AES encryption instruction, and fcos, that's a floating point cosine, and fadd, that's a floating point addition, they can be emulated with other fundamental instructions like move, but they're not as powerful as, let's say, move, because they can't emulate move. So those are less flexible, maybe more useful, but less fundamental than those move instructions and all. So in fact, if you look at a modern general purpose processors, they typically support a combination of multiple instruction sets, typically in the form of base instruction set plus a few extension instruction sets. The image on the left is my is a CPU sitting in my laptop. And if you look closely to the instruction section, you'll see many instruction sets, but really the only EM64T, that's really what's driving most of the programs. Everything else, they are useful, but they are like extension instructions, and they're less flexible compared to those fundamental instructions. The similar thing happens on the right. That's a CPU sitting on something called Milk 5. That yeah, it's of my friends. That's got a RISC-V processor, and if you look at this ISA instruction set architecture row, it's again written R564I. That's a basic instruction set plus some extension instruction sets that's like exclusively available to certain processes. Right, so going back to the executable thing, what if instruction itself has an internal program structure? So that's a special case. That's a really special case when the instruction set itself is like a program, by which I really mean there is a monad prog instance. You can compactify an executable that's a like tree of all the instructions into a single instruction. What I mean is you can actually implement this compactify function that as long as a monad instance is available to the instruction data type prog, an executable prog exit code can be compactified into a single prog of exit code. The implementation isn't so hard. It's actually very simple. We're like literally replacing exits with monad pure and non-empty with flat maps. And I'm not going to go into detail, but notice how similar this is to the inject.exits function, because that function operated on the exit nodes. Now we're operating on like both exit and non-empty in a rather simple way. It's simply a recursive pattern match function. Okay, so that implementation isn't so important. The important bit is that is a fact that we can use the compactify function to leverage a runtime for a monadic instruction data type prog to a runtime of executable prog, to be more precise here. For instance, if we put cats effect IO as prog, then the IO type does have a corresponding runtime in the cats effect library, which is called IO runtime. So we get an evaluator for executable IO for free. Okay, so the question is, what if there are instructions that don't accommodate those program-like structures? What if there are non-fundamental instructions too? Now, right, if you've written any JavaScript in the mid-2010s, or even these days, actually, you probably have seen a solution to this problem already. What happened then was that the specification of a refurbished version of a JavaScript was released, which was ES6 back then, and later renamed to ECMAScript 5. Sorry, ECMAScript 2015. And the problem was, as you may have heard, the Internet Explorer was not supporting ES6. And this was a time when substantial percentage of people was using the good old Internet Explorer, and writing ES6 on your website was sadly not an option back then. Unless, of course, a tool now known as Babel was invented and people could use it to convert or transpile this new ES6 code to ES5 or even ES3, a much older version, to make it work on the older browsers. In principle, Babel scans through your beautiful ES6 code, finds syntax or language features that are only available in newer versions of JavaScript, and then replaces or desugars them to older, more stable and boring constructs that can be run by older browsers too. And that's exactly what we need to do. If we build a kind of a pipeline that takes in a program that contains specialized and non-fundamental instructions, just like AES-Inc., desugars them into sequences of more boring instructions, we're now able to leverage the existing machine to run your program written in a cleaner syntax. Right, so what would this transpiler look like? A transpiler would expand certain composite and non-fundamental instructions into sequences of like boring instructions, but they have to mimic the intention of the original instruction. So the idea is expressing this pseudocode. That's a desugar function that takes a program and sort of flat maps each instruction using a function, which if it's a composite instruction, desugar it, otherwise leave it alone. Okay, this thing looks like doable with either like construct, and that's what we're going to talk next. So to be able to express that a certain subset of instructions is an extension instruction set, we will look at a simple data structure known as either K, or in some other libraries or languages, they're also known as coproduct, like in Haskell. Now, I want to remind you that we're now getting into a bit of an implementation detail. I mean, we have been looking at the implementation details of EFF anyways, but what we've seen so far were kind of canonical. This section, however, looks at one particular way to combine and decompose instruction sets, and there are other more efficient techniques available out there. For example, tagging instructions numerically, so we dynamically know what instructions we are trying to deal with. But as I've been saying all the time, I think looking at one way to implement a thing helps. So let's get into details anyways. So first, we're going to see how we could combine several instruction sets while keeping track of where each instruction is coming from. To do so, as I mentioned, we define a data type known as either K. It takes 3 type arguments, instro1, instro2, and branch index. And it's got a single field of an either instruction1 of branch index or instruction2 of branch index. We'll see in a moment what this all means. The next step is to define an effects type alias, which we call mix. That is essentially a partially carried version of the either K data type. Now, what does this thing do? So you can actually just forget the definition of either K for now, as long as you understand this thing. Suppose we have 2 instruction sets, IS1 and IS2, containing 2 and 1 instruction variants respectively. Now, if we consider the type IS1 mix IS2 on the bottom right corner, recall that mix was an infix type, so you can write it like this. So this type is actually isomorphic to, or in other words, essentially the same thing as IS3, which has got 3 instruction variants, each coming from either IS1 or IS2. For example, C1 comes from I1, C3 comes from I3, and so on. So you can think of the mix type as really mixing 2 definitions of enums and combining them together into one. Not how similar this is, similar the end result of writing like IS1 mix IS2 is to having enumerated base instructions and extension instructions in the CPU inspection tool. Now, of course, the opposite question of how can we mix different kinds of instructions is how can we pattern match against an instruction in a combined instruction sets? This gets a little bit more technical, but we can do what we want to by defining a type class, decompose here we call it, and writing a few type class instances that helps us pattern match on mixed instructions. The decompose type class is a constraint between 2 instruction sets, subinstr and instra, and an instance of decompose subinstr instra states that subinstr is a proper subinstruction of instra. Such an instance must understand the precise set of instructions that will be left over when we take subinstra out of instra. So you see the diagram on the right. This knowledge is encoded in the associated instruction type, the complement. And to allow one to make use of this knowledge, the type class instance must provide a classify method, just one method, which judges if a given instra A is either the subinstra A, which we're interested in, or the non-interesting part of the complement of the subinstra. Okay, so using the example from the previous slide, an IS1 is a proper subinstruction of IS1 mix IS2. So we can write down an instance of decompose IS1 mix IS2, with the complement being IS2, which is the whole thing minus IS1. Okay, so let's write a few rules. I'm gonna skim over this one because it's quite long. So the simplest rule is the case when we want to assert that subinstra is a proper subinstruction of subinstra mix right I. The situation is drawn on the right. It's fairly intuitive that we can actually implement this. And of course, there's an almost symmetric instance that asserts that subinstra appearing on the right is also can also be pattern matched. The situation is like that. The code remains almost exactly the same, except we have to add the last swap at the end. Okay, so the last rule we're going to add is a bit more complicated. What this instance asserts is that whenever instra 0 is a strict subinstruction of instra 1, like that, and instra 1 again is a subinstruction of instra 2, then instra 0 is a subinstruction of this entire instra 2, which sounds a bit obvious. But a nice thing to note is that the definition of complement is actually quite simple. In fact, what you get from removing instra 0 from the entire thing is the pink part, that's the complement of instra 0 and instra 1, plus the light green part, that's complement of instra 1 in instra 2. So yeah, you simply mix them and that's the complement. The implementation kind of follows automatically. I think GitHub Copilot wrote all of this. Yeah, so that was a bit of an implementation detail. We are finally ready to write an actual machine. Before that, we'll see something. So recall the desugar function we wanted to build. The whole point of mix and decompose thing was to make this function available to us. So in order to achieve the desugar function, we'll first define a very general mechanism for transpiling executables. Recall that the job of a transpiler is to replace a syntactic construct with a potentially much longer sequence of simpler constructs. The general transpiler we define will be driven by a rulebook like this, as shown on the slide, which takes an instruction in one instruction set, I1, and sort of expands it to a collection of instructions in another instruction set, I2. An appropriate choice for the collection of instructions would naturally be our beloved executable. So we'll encode the transpilation rulebook as a function that's able to convert any I1 to an executable written in I2. So keeping that in my mind, we're ready to define the general transpile function. So, but at this point, not much work is left. In addition to the transpilation rulebook encoded as the function, we simply take an executable written in I1 and then sort of replace or expand every single instruction in the original program using the transpilation rulebook. And that's it. That's all of a transpiler. And it's really simple to implement too. You only need to touch the non-empty clause, and yeah, that's like 3 lines of code, which you can read later. Anyways, that allows us to convert an executable written in one instruction set to another executable written in another instruction set. And this serves as a basis for the staged transpilation strategy, where each gap in this entire diagram is a special case of transpile call. So you desugar instr 3 into instr 1s and instr 2s, you desugar instr 2 to instr 1s, and then you compactify. You can now run the entire program. And yeah, the implementation isn't that complicated. It's a single call to the transpile function, which I suggest you read it later because we don't have much time. So as a recap, we saw that we can extract the structure out of assembly language and encoded the idea in Scala as a data type we named executable, which is commonly known as EFF. Values of this data type can be composed with the inject@exits function, which, if you've noticed, is actually called flatmap. In order to build a machine that runs executable, we devised an architecture where transpilers are stacked on top of each other. And at the bottom, we are having the base runtime. And we implemented everything with the help of the decompose type class. So I don't think we have much time left to go through the example, but the point is, if you've got a custom instruction like log with level and http get, as long as you desugar them to, let's say, cats effect IO, you can execute the entire program. So these are the definitions for custom effects. For desugaring HTTP GET instruction, you simply take one HTTP GET instruction and replace it with log instruction, and then actually get the entire content in IO context. So that's a single instruction, and then again log how much the result was. You can also desugar log with level instructions. That's a single call to IO.println. Okay. Now we can finally put everything together. If you have a program written in IO mix log build level mix HTTP get, you can pipe through all the transpilers, the first 2 lines there, and then compactify the result. You can finally unsafe run sync the entire thing using IO runtime. Okay, so wrapping up. I didn't cover some stuff today. Like I didn't cover how we can use EFF to write an actual application logic. You normally do this through something called Open Union, which is not really far from where we are. Alternatively, you can do everything with tagless final. Also, the transpilers normally are polymorphic in the instruction set, which also requires something called a member in type class. And finally, I haven't talked about optimization. Actually, our implementation is terrible in terms of performance. Other practical libraries do much more work on improving this. For example, they use something called type align sequences. And some libraries even say that they've got like constant time handler resolution, which I haven't really looked into details on how they work. But anyways, EFF does have limitations too. And in practice, I experienced some issues with high-yield effects. Those are effects like try-catch or parallelism that affects the entire program as operands. And also they lack stack traces. That's kind of crucial, isn't it? And some concurrency primitives aren't available readily. Some libraries do address this, but in order to do so, they often lose the simplicity, or they make some additional assumptions about the base machine. Okay, so finally wrapping up, the takeaway is that EFF has its own beauty and limitations like many other techniques. And the point is to get a feel for the true capability. It really helps to dive into the implementation and look for connections to existing technologies and libraries. So yeah, as I mentioned at the beginning, I think this knowledge is going to help you explore other effect systems too. So yeah, that's the end of the talk. Thank you.
はい、コリーさん、初上映さん、登壇ありがとうございました。では、時間、もう過ぎてます。はい、時間になりましたので、もしご質問ある方は、この後、休憩の時間にお話しされてください。では、改めてもう一度大きな拍手をお願いいたします。
So I like to acknowledge thanks to all these people who helped and also to the translator because I had to pass the entire transcript this morning. So sorry and thank you.